Hello student. So, today we will talk about different types of biological sequence alignment. In the earlier class we had seen the basic fundamentals of sequence alignment and why do we perform sequence alignments. So, continuing to that, today we will see about the what are the different types of alignments methods and algorithms which are used for aligning these sequences. So, there are two types of alignments. One is called pairwise alignment, second is called multiple alignment. The pairwise alignment is further classified in a global alignment, local alignment, end free space alignment and gap penalty models. As you can see, the global alignment is the alignment of sequence 1 with the another sequence when we are taking the entire sequence. In the case of local alignment, a segment of one sequence when aligned with the segment of another sequence is called local alignment. Whereas, in end free space alignment, the tail end of one sequence with the beginning end of the another sequence or suffix of one sequence, prefix of one sequence aligned, they are called a end free space alignments and the two ends are free in that case. And gap penalty alignment is where we are incorporating the gap penalty in the alignment and such alignment is called a gap penalty alignment. So, what is a global alignment? So, the alignment made between the entire sequence of S 1 with the entire sequence of sequence 2, that is S 2, such alignment is known as a global alignment. The global alignment of two sequences S 1 and S 2 is obtained by first inserting chosen spaces either into or at the ends of S 1 and S 2. So, the length of sequences will be the same. For example, given a sequence 1 A C G C T T G and sequence 2 C A T G T A T, the alignment will look like this. So, what are the algorithms required for understanding the global sequence alignments? So, the algorithm is used for global sequence alignment is called Needleman-Wunsch algorithm. This algorithm is based on the dynamic programming and it is an efficient recursive method to search through all possible alignments and find the one with the optimal alignment score. Given a scoring schemes, how does an alignment algorithm works has to be demonstrated by the Needleman-Wunsch algorithm. So, this algorithm deals basically three steps. The first one is called a initialization steps, second is called a recurrence steps or matrix filling step and the third one is called a trace backing steps. So, in the beginning the alignment begin with the 0th row and 0th column and for that 0 value is given and then in the base condition in initialization the first rows and first columns is filled and recursively then the recurrence condition is used to fill the complete matrix. So, initializing this condition you have been given a two sequences as you can see in the pictures. The two sequences one is a vertical axis, the other one is a horizontal axis. So, the 0th row and 0th column is inserted. So, V 0 0 is equal to is given a 0. In this case the match has been taken a plus 1, the mismatch has been taken a 0 and indel value has been taken a 0 score. So, in the initial stage we have to sum up all the values of the previous in the 0th rows and 0th column, so that we can initialize this matrix. As you can see the first row and the first column is the 0th row and 0th column, all the values are 0. So, initializing the values as we can see the matrix can be filled by three ways. You can see we need to have a I minus 1 comma j minus 1 cell. This value has to be filled by the diagonal or vertical or horizontal. If the value is coming from diagonal, it is I minus 1 comma j minus 1, the current value should be I j, and if it is coming I minus 1 comma j or I comma j minus 1, it is a horizontal and vertical. So, the current value can be filled from this value. So, this is a recurrence condition and as you can see the second rows, that is a first character row and the first column character, the three previous values are known and from the three previous value you can fill the value in the current cell considering match, mismatch and indel values. As you can see the first matrix where the current value can be filled by this recurrence condition. You can go back to the previous slides where you can see the recurrence conditions. This equation V I comma 0 is equal to summation of sigma S I comma gap. The second one is called a V 0 comma j is equal to summation of 0 to j and the sigma gap comma T j. So, this is used for filling this matrix. As you can see, the matrix is being initialized and recursively the second row, second column, then third row, then third column, the value can be filled. As you can see that 0 has been taken for initialization, 0 has been taken for indel values and 1 has been taken for the match. So, diagonally you can see the 1 value is coming 1 from the in the first character, in the second matrix you can see it is a 1 which is represented in a red color. So, it is coming from the diagonal because G and G is match character, and similarly you can fill all this value recursively, and finally you will get in the last the matrix, the filled matrix, and in the filled matrix the last cell, that is the matrix value, the maximum value is 6, you can see is obtained in this global alignment. So, the third step is trace backing from where this value is coming. So, you have to start from the last cell and you have to find from which previous cell, whether it is a diagonal or vertical or horizontal cells this value is coming. So, recursively you can find from where this value is being derived, and finally, you can draw a diagonal run. So, you can in the trace backing you have to go from the last cell to the initial stage of the 0th rows and 0th column. This way you can align your sequence. Here another case example has been taken where the match has been taken a +5, mismatch or substitution has been taken a -2 and indel value has been taken a -6. So, the two sequences here are x source, y target. You can think like this also, you can say like that also, that sequence 1 and sequence 2. So, here the indel value has not been taken a negative value. What I mean to say here, in the global alignment one can take the indel mismatch substitution value negative or positive value, and the match value is a +5 in this case has been taken. So, you see when you are taking these two sequences, the red color shows the trace backing steps, and the first row you can see the 0 and the indel value has been taken a -6. So, recursively it is being summed up -6, -12, -18, -24, and similarly in if you go in the column you can see that 0, -6, -12 and -18, and similarly it will keep on going. And in the recurrence conditions you can fill the matrix by taking these three condition match, mismatch and indel value, and finally you will find the rightmost corner 11th is coming the optimal alignment score. So, once you get this value, how do you know that the value is 11? So, again you have to align the sequence from trace backing steps. So, what you do in this trace backing step? You align the row, the A character sequence y with the A character of sequence x. So, these twos are match. So, this match value will come from diagonal. So, you will go to the diagonal, and you can see when in the alignment the A is matching with A, it has been given a +5, and similarly T is giving a diagonal, it is a match of +5, and similarly the other values A where the mismatch case is there, it is coming from diagonal, and similarly the another value C and C is a match which is coming from diagonal, then T and T is coming from the diagonal, and then there is a insertion of two characters in the sequence 2 C and G, and that is why they are aligned with the gap, and it finally match with the T and T and ends at the 0th rows and 0th cell. And then you align these two sequence and sum of these values, you will see the match score will be given a +5 and the mismatch it is giving a -2, and the match again +5, then T and T is a match, and the gap and C, gap and G is a -6, and again the match T and T. So, finally, you will get the 11 total score. Here another case of two protein sequences has been taken, but in this case the score has been taken based on the substitution matrix value. You can see the left side of the image how the matrix has been filled considering the values based on the substitution scoring matrix, and the right side the matching score value has been circled which has been taken. So, here the two possible alignment score, you can see from both of them one can get one values, the left hand side and right hand side. So, there are two or more than two optimal alignment path you can find in a sequence, but ultimately you have to select one path for that. The alignment graph is a directed acyclic graph. So, in the figure one can see the segment of the alignment graph, which represent the three possible at each stage of the algorithm. The second alignment type is a local alignment, which is also known as a Smith-Waterman algorithm. Given a two sequence, a part of one sequence with the part of another sequence, or a segment one sequence with the segment of another sequence, when aligned, such alignment is known as a local alignment. So, here a case has been taken alpha, which is a part of sequence 1, and beta the part of sequence 2 or sequence target, whose alignment has been shown by the edit operation value considering match plus 2, indel substitution minus 1, and the best alignment is shown here in the red color, alpha and beta, which belong to the alpha belong to the part of source S and beta belong to the part T. The method is useful for comparing the following. So, protein sequences that shares a common motif, conserved patterns or domain independently folded unit, but differ elsewhere. Second, protein sequences against genomic DNA sequences, which is the long stretch or uncharacterized sequences, DNA sequences that have a similar motif, but different elsewhere. How one can compute the local alignment? So, again it has a initialization steps, recursive steps and trace backing steps, but here the condition for local alignment computing is a very important when we are trying to analyze the optimal alignment score Vij, which denotes the value of the optimal local suffix alignment for a given pair I j of the indices, where the limitation is the score x y is equal to greater than equal to 0 if x and y match. It means one cannot take the negative value when the characters are match, whereas in the global alignment one can take that if it is a even less than 0, but not in the case of local alignment. The second condition is that if x and y do not match or one of them is a spaces, it should be less than equal to 0. So, the scheme of the algorithm compute the local suffix alignment, and for all the value of I and j of sequence 1 and target sequence T 1 to j and for source sequence 1 to I. So, this is done using the same procedure as we have seen in the global alignment, initialization, recursive and trace backing. Second, search the results and find the indices I star and j star of source and target respectively, after which the similarity only decreases. So, again the formula is for calculation of the local alignment, the initialization condition is for all value of I and j, the V I 0 is equal to 0 and V 0 comma j is equal to 0, and the recurrence conditions you have to take the maximum value of diagonal, vertical, horizontal, and if from these three the value is coming in negative, they will be substituted by maximum value 0, as we can say we have to take the maximum value from all this, where 0 is also given in this conditions. So, to compute the I star and j star optimal alignment score V I star j star, which is the maximum of the range of I 1 to n and the range of j 1 to m of V I j. Observe that the recurrence for computing local alignment is almost identical to the one used for computing global alignment. The only difference is the inclusion of 0 in the case of local suffix alignment. So, here again case studies where one can take two sequences, here two sequences has been taken, and in the penultimate rows the value is maximum, and from there the trace backing start, and wherever the 0 comes the trace backing stops. So, 0 in the base conditions and in the recurrence relations allows the alignment to start anywhere in the sequences rather than forcing it to start at the beginning of each. So, searching for I star and j star, the maximum alignment score that gives the best V I star j star, that gives the best alignment, allows the alignment to end anywhere in the sequences rather than at the end of each. Here is another sequences which has been taken, source and target, and you can see the two sequences are giving a match from trace backing stage GAA in X and Y GAA. So, for match one value is given here. So, that is why the 3 value is coming in the matrix cells. So, the complexity of this local alignment algorithm is big O n into m, and the space complexity is big O n plus m, because in the time complexity it takes only big O m into n, but time to fill the entire table, the search for the V I star j star require only O big O n into m times as well. Therefore, the time complexity is a big O n into m. So, if we compare the Smith-Waterman-Needleman-Wunsch algorithm, the Smith-Waterman algorithm is a local alignment, Needleman-Wunsch is a global. It requires a gap penalty to work effectively, whereas Needleman's gap penalty not required. The Smith-Waterman algorithm required a no negative scores is used in the initializations, whereas no such condition in the Needleman. In a Smith-Waterman algorithm, find the regions of ungapped sequences with a high degree of similarity, whereas in the case of Needleman's it is compare sequences and gives best overall alignment. Local alignment is useful for finding the higher similarity match, to find the local regions with the highest level of similarity, suitable for aligning more divergent sequences, find conserved patterns in the gene or protein. There are other parameter when we are aligning the local sequences, which is a maximal segment pair, which is a ungapped local alignment whose score cannot be improved by extending or shortening the alignment. Second one is a locally maximal segment, which is a segment whose alignment score without gap cannot be improved by shortening or extending it. The third one is a high scoring segment pair, which is a maximal segment pair with a score S between source and target, where ST source and target is a similarity score threshold, typically user defined. The third category is a alignment is end space free alignment. So, any number of indel operations at the end of the beginning of alignment contribute 0th weight. This drops the requirement that sequences start and end at the same place and allows us to align sequences that overlap, include one another. Here example has been taken. Consider the sequences, the two sequences source and targets. There are 3 possible ways it has been aligned, which has been shown in the blue and red color. The third condition, which has been indicated in red color, the source and target, where the one in suffix of the target and prefix of the source has been aligned. So, the end space free alignment algorithms, they are also like global and local initialization, recursive and trace backing steps. So, the initial condition allows 0 weight to lead indel operations in at most one of the sequences. After filling the table with the values V I j, one can search for the maximal value in the either of the ending rows, that allowing at most one sequence to end before the other with 0 weight for all indel operations from there on. This value is the best value. The aligned sequences is tracked using pointers created while filling the tables from cell 00 in the table until the end of one sequence, which can be seen in the figure. नहीं बैक जाइएगा, वहाँ पर लास्ट लाइन मेरा थोड़ा सा करेक्शन करिएगा, वो फिगर यहाँ पर नहीं है, लरा हटा दिए. The aligned sequence is traced using pointer created while filling the table from cell 00 in the matrix until the end of one sequences, the bottom rows, rightmost column. From there on, all indel operations until the last cells are not counted in the total value through they are present in the matrix. What is the motivation behind such end space free alignment? The two sequences will have high score if they possesses an overlapping section by end space free alignment, while gives less score by global alignment score. As you can see, this is the overlapping segment which are coming from the shotgun sequence assembly. The one end of sequence aligned with the second end of the sequence. For example, here A T C G aligned with the C C G A C, where the suffix of sequence 1 aligned with the prefix of sequence 1 characters. So, this is the conditions of recursive condition, how to calculate. As we have seen, the first base condition for all the value of I and j, it shall be the 0, and the recursive condition is similar to the global alignment, and again one has to search the I star and j star value, which is maximum of V I j, and finally one has to find the optimal alignment score V S T, which is the maximum of V n comma j star and V I star comma m, that is the last row and last column. Here it can be seen in this matrix, the last row and last column, the maximum value is aligned starting from the last cell, considering match is equal to 2 and indel and substitution is equal to -1. The complexity of end space free alignment is, for time complexity it is a big O n into m, and space complexity is a big O n plus m. Till now we had discussed about the pairwise sequence alignment. Now we are considering the multiple sequence alignment. When alignments made among 3 or more than 3 sequences, it is known as multiple sequence alignment. As here one can see that there are total 5 sequences has been taken, and where is the conserved regions which are highlighted has been shown, that is a case of multiple sequence alignment. So, for multiple sequence alignment, scoring is important, and for scoring sum of pairs of scoring, which is a columns are scored by sum of pairs, which can be calculated by using the substitution scoring matrix, and the formula for this one is S m I is equal to summation of k less than L S m I to the power k m I to the power L, where m I k is equal to the character of the kth sequences in the ith column. So, S is the substitution scoring matrix such as PAM or Blossom matrix. Here 3 sequences has been taken for alignment, sequence 1, 2 and 3. The sum of the second column is equal to score k r plus score r h plus score k h is equal to 2 plus 0 minus 1 is equal to 1, and this value has been taken from the substitution scoring matrix. So, multiple alignment methods are 3 types: dynamic programming based, progressive alignment, iterative refinement. So, multiple sequence alignment, which is based on dynamic programming, is a Needleman's Wunsch algorithms can be generalized, and it calculates the sum of the column of scores S m is equal to summation of S m I, and there are a indicatives f I 1 to I 2 to I n sequences, which represent the optimal alignment up to the I 1 to I n. The optimal score of alignment of the first sequence I 1 letters align the I 2 letters of the sequence 2 letter to the sequence n, and so on. F I 1 comma I 2 till I n is equal to the maximum of all neighbors of cube multiplied by the f neighbor multiplied by the s neighbor. In 2-dimensional dynamic programming, there are 3 previous neighbors. In 3-dimensional dynamic programming, however, there are 7 previous neighbors generalized to the equations 2 to the power k minus 1 for k dimensional. So, dynamic programming for multiple sequence alignment can be seen by this equation f I comma j comma k is equal to maximum of all these value, which can be seen in these equations. The problem with multi-dimensional dynamic programming is that it is a completely unscalable for more than 3 sequences. The size of dynamic programming matrix is L to the power n, where L is equal to length of each sequences, n is equal to number of consequences. The second method is called progressive alignment, which calculate k 2 to k pairwise alignment scores and convert them to distance. It uses an incremental clustering algorithm to construct a tree from the distance, and the third one is a traverse the nodes in their order of addition to the tree progressively aligning the sequences. So, progressive alignment In the third step, it traverses the nodes in their order of addition to the tree, progressively align the sequences. This way, the most similar pair is aligned first, followed by addition of the next more similar or set of sequences. The features of progressive alignment is the order of aligning of sequences or set of sequences is determined by their highest scoring pairwise alignment. Once a gap, always a gap, which is replaced in alignments by neutral character. So, as one can see in this hierarchy, in progressive alignment, align the closest profiles or sequence first. At each alignment, align two sequences, as in this figure one can say x y are profiles p x p y to generate a new alignment with a profile p results. One can use a weighted version of the tree in which the weight of the edge is proportional to evolutionary divergence in that edge, and the new profiles is weighted average of the two joint profiles. A profile is when you take pairwise multiple alignment and convert it into the vector of the probabilities. You can see in this hierarchy that C and D is clubbed by P D and A and B clubbed, giving the probability A B, and probability of C D and probability of A B resulting the probability of A B C D. The third one is called iterative refinement. Iterative refinement addresses the problem in progressive alignment that the initial alignments are frozen despite new evidence coming in that should change the original alignments. For examples, you can see that x, y, z, w, the four sequences. In this example, x and y are frozen, but if you observe z and w, it is clear that the gap in y should be placed such that y is equal to G A gap C T T. So, what are the uses of multiple sequence alignment? It is used for highly conserved or similar regions closely or distantly related motif within a set of related sequence, detection of structural homologies, patterns of hydrophobicity, hydrophilicity, gap, making patterns or profiles that can be further used to predict new sequences falling in a given family. Computing consensus sequences. It is also useful for inferring evolutionary trees or linkage. It also provides stronger evidence that pairwise similarity for structural and functional inference. It serves as the first step in phylogenetic reconstruction, in RNA secondary structure predictions, and in building profiles for protein families or DNA signals. Dear students, thank you very much.